IMFs exist between any two molecules that are close to one another. We often think about IMFs within a pure substance. This water molecule and this water molecule, how strongly do they attract one another? That's what gives water its properties: its melting point, boiling point, vapor pressure, surface tension. All of those are based upon within that pure substance, how strongly can the molecules attract. That's true about things whether they're polar or nonpolar, whether they exhibit hydrogen bonds or not. But we can also describe the properties of things when I have a molecule of one compound and a molecule of another compound. They either attract one another strongly or weakly. If both compounds that are mixed together are nonpolar, then the strongest and only attraction that would exist between them would be dispersion forces. Both of them have electrons that can move around, and therefore both of them would attract one another based on those temporary dipoles and the induced dipoles. If I have two polar things like HCl and HBr, those two are polar and would attract one another with dipole-dipoles. They would have maybe different magnitudes of their dipole, but there would still be a positive attracting to a negative and a negative to a positive. If I have something like ammonia, NH3, which has nitrogens bonded to hydrogens, and water, H2O, which has hydrogens on oxygens, the attractions between those molecules could be hydrogen bonding. The nitrogens lone pairs and negative dipole would attract to the positive parts of the water, the hydrogens, and the negative dipole on the oxygen would attract to the positive dipole on the hydrogens. But we can also mix two things that are not necessarily similar or the same in what type of molecule or compound they are. Probably the most important of these in terms of understanding properties, or the one we're at least most familiar with, is an ion to dipole interaction, or ion to dipole, most of the time, attraction. When I have an ionic compound, salt as an example, it dissolves in water. The reason that it dissolves is that we can make attractions that are strong enough between the two separate particles that keeps it mixed together. The reason that that attraction can be made is that our ion has a positive or negative charge, sometimes even positive 2, 3, or 4. That positive or negative charge is the Q in Coulomb's law. The larger that positive charge, the higher the attraction between the ion and the polar molecule. The polar waters arrange themselves very specifically with the negative end of the dipole next to any positive ions, the positive end of a dipole next to any negative ions. The larger my cation or anion, the farther apart these would be for a smaller attraction, and the smaller ones would be a larger attraction. So whether I'm doing hydrogen bonds, dispersion forces, ion dipoles, it all comes back to Coulomb's law. What are the charges and how far apart are they? The closer they can be, the stronger the attraction. The higher the charge, the stronger the attraction. So one important piece with this is because an ion has either a full +1, +2, or +3, sometimes even more charges, that is a larger Q value than anything we would see with polar or nonpolar. The ion to dipole forces are often stronger than other types of IMFs. That can vary with size, but it's important to remember that that ion does have that full charge. Ions can also be placed into nonpolar solutions. That ion would still either have a full positive or negative charge. In this case, we're still using a cation, a full positive charge. Well, that full positive charge would pull electrons towards itself. It would distort our electron cloud, causing a temporary or an induced dipole on our nonpolar compound. They're generally distributing equally, but in this case, it would be distributed unequally. That attraction's weaker than the ion to dipole because our polarity is not as big. It's not quite as permanent or as strong of an interaction. And that's why we would see a difference inability of an ionic compound to dissolve in something nonpolar compared to polar, but there is still an attraction. The last of these types is a dipole, something that is polar, like water, a permanent dipole, attracting something that is not polar. So polar and nonpolar things we often describe as not mixing. Oil and water don't mix, but there is attractions between them. The permanent dipole, the thing that we've made polar, the negative part repels electrons and pulls the positive a little bit closer, and vice versa in terms of the positive end of my dipole with the electrons. So it polarizes my nonpolar thing. In both of these cases with induced dipoles, the more polarizable your nonpolar molecule, the stronger that attraction can be. But these tend to be weaker than the attractions within like a pure dipole to dipole. As we talk about things that do and don't dissolve, we'll come back to this, but this interaction is important. The oxygen in this case would attract another oxygen with only dispersion forces. The water to oxygen makes a permanent to induced or a dipole to induced dipole. That actually is a slightly stronger attraction because the charge here is bigger and it can induce a slightly larger dipole than the temporary one. But a water attracting another water is a dipole to dipole that is permanent. In this case, in fact, it's even a hydrogen bond. So the fact that things don't mix doesn't mean that there's no attraction. It's just about which attractions are the strongest and how does that allow things to stay together. So identifying the IMFs within a pure substance is very important. And then taking that to recognize what IMFs would exist between the two substances is also important whenever we have a mixture.